Welcome to this video on reacting mass calculations or finding the maximum theoretical mass of a substance in a reaction. Before watching this video, you will need to know how to calculate the relative formula mass of a substance, or the MR. I will refer to it as the MR throughout this video, so just be aware that that means the relative formula mass. How to balance a symbol equation, and how to use the mole equation. The mole equation is shown here as a triangle and also as an equation down below. Just remember when you are using this that the mass must always be in grams. So if you are given a question where it is in kilograms or milligrams or something else, you must be converting back to grams. So very quickly, we're just going to talk about molar ratios and stoichiometry. So the stoichiometry tells you how many moles of different substances are needed in a reaction. So in other words, it's the big numbers in front of the substances in a balanced equation. So here, this reaction shows ammonia being formed by the reaction of nitrogen and hydrogen. And my balancing, or my stoichiometry, tells me that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. So in my reaction mixture, let's say I actually had 4 moles of nitrogen. To react with the 4 moles of nitrogen, I would need 12 moles of hydrogen because my ratio is 1:3, and that mixture would produce 8 moles of ammonia. Another example, if I had, let's say, 100 moles of nitrogen, I would need 300 moles of hydrogen, and it would produce 200 moles of ammonia. And a last one, if I had 0.5 moles of nitrogen, I would need 1.5 moles of hydrogen, and I would produce 1 mole exactly of ammonia. Another example, just a slightly more complicated ratio. This is showing ethane, C2H6, reacting with oxygen in a combustion reaction, a complete combustion reaction, to produce carbon dioxide and water. So my ratio here, my stoichiometry, tells me that 2 moles of ethane reacts with 7 moles of oxygen to produce 4 moles of carbon dioxide and 6 moles of water. I could simplify that a little bit and say that 1 mole of ethane reacts with 3.5 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. So using this ratio again, let's say I had 4 moles of ethane, so I've times my 1 by 4, that would give me 14 moles of oxygen are required, because 3.5 times 4 is 14. I would produce 8 moles of carbon dioxide, and I would produce 12 moles of water. And a final one, if I had 0.25 moles of ethane, I would need 0.875 moles of oxygen to produce 0.5 moles of carbon dioxide and 0.75 moles of water. So if we look at our actual questions, I'm going to show you 2 methods using the same questions. This first method is what I would say is like the real method that shows your understanding of the stoichiometry, and the second method is more of a cheat method. But we're going to look at the same questions for both methods. So my question here is: aluminium oxide decomposes to form aluminium and oxygen gas according to the equation below. What is the maximum mass of oxygen produced from 45 grams of aluminium oxide? So firstly, I would just summarise what information you have got. So I'm going to use green for the aluminium oxide, and my question tells me that I have got 45 grams of this, and my question is asking what mass of oxygen will I produce in this reaction. So as well as having a mass, remember that if you have got the symbol, or you can work out the symbol, you have also got the MR, the relative formula mass. So my relative formula mass of aluminium oxide is going to be 102 grams per mole. And for my oxygen, my MR is going to be 16 times 2, 16 being the atomic mass of oxygen, is going to be 32 grams per mole. So in this case, we don't need to think about our aluminium, so I'm just going to cross that out because we're not interested in it. So for my aluminium, I'm going to use my grams, my mass, and I'm going to use my MR to work out how many moles I have got. So I'm going to draw my triangle, and here I've got 45 grams, and I'm going to divide that by 102 grams per mole. Now this gives me 0.441 moles. So 45 grams is equal to 0.441 moles. I'm then going to use my molar ratio within my equation to find out how many moles of oxygen, so I draw another triangle for oxygen, I produce in my reaction. So my stoichiometry in my question tells me that for 2 moles of aluminium oxide, I am going to produce 3 moles of oxygen. Or on the other hand, a simpler ratio would be 1 to 1.5. So I'm going to times my moles of aluminium oxide by 1.5. And that gives me a value of 0.662 moles. I know my MR because I worked that out earlier, and that is 32 grams per mole. And if I multiply those together, I get a mass of 21.2. So my maximum mass of oxygen that is going to be produced from 45 grams of aluminium oxide is 21.2 grams. And that is my answer. Okay, we're going to look at another example using this method, but in this case, the question is asking for the minimum mass of a second reactant needed. So methane, which is CH4, burns completely in oxygen to form carbon dioxide and water according to the equation below. What is the minimum mass of oxygen needed to react with 113 grams of methane? So again, I'm going to summarize what is told to me in the question. So I know I have got 113 grams of my methane. Again, I can work out my MR, which for methane would be 16, for 12 for one carbon, and then 4 for the 4 carbons. So it's going to be 16 grams per mole. And my question is asking me what mass of oxygen is needed to react with this. And again, from the previous slide, I know that my MR of oxygen is 32. So I'm going to need some triangles again. I'm going to do them slightly bigger because it was a bit small before. So here I've got 113 grams of CH4, methane, and I'm going to divide that by 16. That gives me 7.06 moles. Okay, and again, from my equation, I can see that my ratio of methane is 1 to 2. So whatever the moles of methane is, I'm going to need double that for the oxygen. So I'm going to times that number by 2. Okay, and for that value, it is 14.125. Just for space, I'm just going to put 14, but in my calculator, I've left 14.125, and I'm going to multiply that value by my MR of oxygen, which is 32, and I get 452 grams. So the minimum mass of oxygen that I needed to react with 113 grams of methane is 452 grams. So that's my answer. If I had any more than that, my oxygen would be in excess. If I had any less than that, my oxygen would be the limiting reactant, and I wouldn't have enough oxygen present to fully react with all my methane, with that 113 grams. So I'm now going to show you what I call the cheat method for the same questions, and you'll see we get the same answer. There's just kind of fewer steps, or actually there's the same number of steps, you just do them in a slightly different order. So again, my aluminium oxide decomposes to form aluminium and oxygen gas according to the equation below. What is the maximum mass of oxygen produced from 45 grams of aluminium oxide? So again, start off the same. I'm going to summarise the information I've got here. So I've got 45 grams of aluminium oxide, and I am after my mass of oxygen that is produced. So here we're going to calculate our MR again, which was 102, as it was in the previous version of this question. However, what I'm going to do is I'm going to multiply my MR by the stoichiometry. So I'm going to do 2 times my MR. Okay, and so that gives me 204 grams per mole if we're keeping the units the same. And I'm going to do the same thing for oxygen. Here, I'm going to do 3 times my MR. And in doing this step here, we don't have to use the ratio in the same way that we did in example 1. So 3 times my MR was 32, if you remember. And so that gives me 32 times 3, that is equal to 96. So I'm going to use my triangles again. So in this case, I'm going to do 45 divided by 204. And that gives me a number of moles that is 0.22. Again, if there's more significant figures in that, leave them in your calculator for the next set. I'm just condensing them down due to space. So rather than doing the ratio again, I'm just going to get another triangle for my oxygen. And I'm going to immediately put the same number of moles in there, so 0.22. And rather than having to mess around with the ratio, I'm just going to multiply it by the 3 times my MR for the oxygen, so 96. So if I do 0.22 times 96, I would get 21.2 grams. That's the exact same answer that we got during method 1, but we've just sorted out our ratio by doing our multiplications at this point. So again, my answer is 21.2 grams, which is the same answer as we got in example 1. So I'm going to do the second question using the same method. So here, my methane, I've been told I've got 113 grams. And actually, in this case, my stoichiometry tells me I've got 1 mole of this. So 1 times my MR, which is just 16 grams per mole, as it was before. And then for my oxygen, I know this is what my mass I am calculating. And according to my stoichiometry, I've got 2 of them. So I'm going to times my MR by 2. So 2 times my MR, which is equal to 32 times 2, so 64. So if I go straight to my triangle for my methane, let's draw that. I'm going to do 113 divided by my 16, which gives me, again, the 7.0625. And like I said before, in the last example, I don't have to sort out my ratio. I just pop that number of moles straight in my triangle for my oxygen and times it by the 64, the one that's already been doubled according to the stoichiometry. So if I multiplied those together, I would get the same number as before, so 452 grams. So exactly the same as I did in the first method. So in this one, you just, instead of sorting out your ratio after you've done your first mole calculation, you times the MR of whatever it is that you're calculating by the stoichiometry. So in this example, we timed the MR of methane CH4 by 1 because there is no number before the methane, which tells us we've only got 1. So I did 1 times the MR. And then for the oxygen, I did 2 times the MR because my equation tells me I've got 2 of them in my reaction. So I hope you found that a good video to use. So just remember that the molar ratio or stoichiometry tells us the proportions of substances needed to react in a chemical reaction. We can use the molar ratios to calculate the maximum mass, which was our aluminium example, or the minimum mass of a second reactant needed in a reaction, which was our methane and oxygen example. If you were going on from there, your maximum mass could then be used in a percentage yield calculation. And to do that, you would do your actual mass that you've got in your reaction when you did it, divided by your maximum mass that you've calculated, and then times it by 100. So, for example, in the aluminium example, we worked out that our maximum mass would be 21.2 grams, but let's say we got, actually when we did it, we only got 18 grams. We would do 18 divided by 21.2, and we would times that whole thing by 100. Thank you.